So what we're trying to learn about for class on March 14th is to try and understand how it is that we interpret the expansion history of the universe and what that tells us about the fate of the universe. One analogy I want you to keep in mind throughout this thinking is that of a ball or a rock being thrown up into the air. Let me illustrate. So I have a rock here, and you're all familiar with what I normally do with rocks, right? So I'll throw it up in the air. So if I throw it with a relatively small amount of energy, the rock goes up and it comes back down. Remember, when I let go of it and it's heading up, it goes off with a certain velocity. Then it decelerates because of the gravity of the Earth pulling it back. And eventually the deceleration because of gravity overwhelms the initial velocity that it has, and it starts accelerating back towards the ground, and I catch it again. If I throw it harder, it goes up higher. So if it has more velocity going up, the acceleration is the same, and then it takes a longer time to turn around. If I throw it up very hard, then it goes even higher because the initial velocity is that much larger than the acceleration is that much larger than the acceleration that's trying to slow it down. This animation shows another example of this, or a more extreme example of this. So if you fire it with a certain velocity, the cannonball makes it up to a certain height, and then manages to, turns around because of the acceleration of gravity, and then comes back down. If I fire it with more velocity, it continues to go rather higher, but still the acceleration from gravity is high enough to turn the cannonball around and to make it to return to the Earth. If you fire it with a little bit more velocity, it escapes from the Earth's gravitational pull and will travel away from the Earth forever. So in the same way, the fate of the universe depends on the amount of material in the universe. For a universe that has a lot of matter in it, the pull of all the matter on all the other matter is sufficient to slow the collapse or slow the expansion of the universe to the point where then it stops expanding and eventually recollapses. This is what happens to a universe with an awful lot of matter in it. This is analogous to a rock that you throw up with not enough of a velocity to escape into space. The critical universe has just the right amount of material in the universe to slow down the expansion, but not quite enough to cause it to recollapse. And so it's exactly at the right level, or the amount of material is exactly at the right level to keep the universe continue to expand, but at an ever slower rate. It's like the escape velocity from the Earth. If you reach exactly the escape velocity, then you'll just escape from the Earth. You'll always be going away from it, but slower and slower as time goes on. So in the coasting universe, there's not enough gravity to stop the expansion of the universe, and so just like a cannonball with much larger than the escape velocity, it continues. The cannonball will escape, and in the coasting universe, the universe will continue to expand forever. One subtlety that I do want you to think about, and we'll think about this more in class, is that you'll remember that we measure the expansion rate of the universe today. We measure the velocity, or the rate of expansion, essentially the equivalent velocity of galaxies, per unit distance. That's the rate of expansion. So we measure the rate of expansion of the universe today. So you'll notice in all these three cases, the rate of expansion, the gradient of this line, is the same. But how that gradient changes through time, as you go back in time or as you go forward in time, depends on the amount of stuff in the universe. This is one reason why we try to understand the mass and energy content of the universe, because it tells us whether we have this kind of history of the universe or whether we have this kind of history of the universe.